The next application that we want to consider in 3.4.4 is related to optimization. Optimization is the process of finding a maximum or a minimum. This is a really central problem in mathematics. For example, let's suppose that you run a company. You may have the goal to maximize profit and minimize cost, and you can do some analysis to figure out exactly where those optimum values are. Now, if you're dealing with a quadratic function, which graphs as a parabola, then the vertex is going to give you that information. If the parabola opens up, now remember, if the parabola opens up, the vertex is a minimum value. And if the parabola opens down, we'll just visualize it here, that makes the vertex the highest point or a maximum value. Now, every vertex has two components, an x component and a y component. And in the context of an application, both the x component and the y component have an interpretation. So just a heads up, as you begin to work the homework in this section, don't be intimidated by the word problems. If the word problem asks about a maximum or a minimum and poses two questions, then it is simply asking about the x value of the vertex and the y value of the vertex. Example 4, a firework is launched from ground level with a muzzle velocity of 144 feet per second. The height, s, of the firework, t seconds after launch, can be modeled by the function s equals negative 16t squared plus 144t. When will the firework reach its maximum height? And what is that maximum height? Okay, so you are launching fireworks. Notice this problem said that we are launching the fireworks from the ground. So that tells us, let's get a bright color here. The firework's going to launch from the ground. It's going to go up. It's going to follow the parabolic path. And hopefully it will explode at the very height of the path, right? That's the goal, so that more people can see it. You don't want it coming too far this way or exploding too early to injure anyone. We want to make sure that it explodes at the optimum point on this parabola, which is the vertex. This particular path is modeled by s equals negative 16t squared plus 144t. Notice the y-intercept of this function is 0 because we are launching this parabola, launching from ground level. Notice it says the muzzle velocity is 144 feet per second, and really that's all that I need to know to write this model. Notice that 144 is right here. Again, the y-intercept is 0. And as I mentioned previously, this is the gravity term. So as long as I know that information, I can write a function which will tell me the location of that firework at any point in time after launch. So the question posed here is an important question. If we're designing these fireworks, we want to design the fuse so that it's just long enough to burn in order to launch that firework to the vertex so that it explodes at the vertex. So the first question is, when will the firework reach its maximum height? And the second question is, what is the maximum height? Well, notice our vertex has two components. It has an x component and a y component. Or in the case of the variables used here, it has a t component and an s component. Well, what are t and s? T is time in seconds, and s is height in feet. So when the question says when, that's saying what's t? When will the firework reach its maximum height? Well, we know it reaches its maximum height at the vertex. So to answer the question when, I need to find the first component of our vertex. Let's answer that question first. So we're going to evaluate t equals negative b over 2a. So in this case, b is 144. A is negative 16, so we need to evaluate, canceling the negatives, 144 divided by 32. I'm just going to type that into my calculator, 144 divided by 32, and we get 4.5. So 4.5 seconds after launch, our firework is going to reach its maximum height. So this is 4.5 seconds. Now the next question says, well, what is the maximum height, right? What is it? Well, it's asking me what's the height of the vertex. So all I need to do is find the second component of my vertex, and we do that by calculating f of negative b over 2a, or in this case, f of 4.5. So we're going to plug 4.5 in for t and calculate. I'm going to use my calculator to approximate. Negative 16 times 4.5 squared plus 144 times 4.5. Whoops. And we end up with an exact value, 324 feet. So our height here is 324 feet. So again, if you were designing this firework, you'd want to make sure that the fuse burns for exactly 4.5 seconds, that it is launched at 144 feet per second, and then it would explode 324 feet above the ground. So let's go ahead and officially answer the question that was posed. The firework reaches a maximum height of 324 feet at 4.5 seconds after launch. You didn't know it, but you are becoming a rocket scientist, right? And it's not too bad. Again, let me remind you, don't be intimidated by the word problems. If there are two questions that are posed regarding either a maximum or a minimum, think vertex, right? One question pertains to the first component of the vertex. The second question pertains to the second component of the vertex. Let's try example 5. While working for a company that produces soccer balls, you are asked how to minimize cost of production. You know that the more soccer balls that are produced, the cheaper the unit price will be. However, producing too many will make the cost of storage increase. Working with the data department, you determine the cost in dollars of producing X 100 soccer balls can be approximated by C of X equals 0.3x squared minus 60x plus 23,000. What production level will minimize the cost, and what is the minimum cost of production? The first thing I want to draw your attention to here is the word minimize and minimum. When I hear those things in combination with a quadratic function, I need to be thinking about the vertex, right? So our function is C of x equals 0.3x squared minus 60x plus 23,000. So let's identify what the variables represent. That's an important way or strategy of answering the question. So notice it says x is in hundreds of soccer balls, and the cost, C, is in dollars. So making a note here on our function, x is hundreds of soccer balls, and the output is cost in dollars. Okay, so if x is 1, I'm not producing 1 soccer ball, I'm talking about 100 soccer balls. Or if x is 2, that's going to give me the corresponding cost of producing 200 soccer balls. So the question says, what production level will minimize the cost? That's basically saying what x value will minimize our cost. This means we need to find the x component of our vertex. And don't forget, that is calculated as negative b over 2a. So b is negative 60. We have negative 60. There's b, divided by 2 times a. Or we have positive 60 divided by 0.6. Let's type that into our calculator. 60 divided by 0.6, and we obtain 100. So x equals 100. Now remember, Very importantly, X is in hundreds of soccer balls. So this means we have 100 hundreds of soccer balls, or you can think of that as 100 times 100 soccer balls, or 1 with 4 zeros, 10,000 soccer balls. Okay, so to minimize the cost, that means we're producing in bulk, but we're not using too much storage. We have 10,000 soccer balls. Let's finish the question by figuring out the minimum cost. The minimum cost is F of negative B over 2A, right? So in this case, it's C. F of negative B over 2A. Our F in this case is called C. Negative B over 2A was 100. Be careful here. I'm plugging in the X value, which represents 10,000 soccer balls. I'm not plugging in 10,000, okay? So plugging that in, we have 0.3 times 100 squared minus 60 times 100 plus 23,000. This particular function is written this way so that I can model a very large number of soccer balls, but my functions has small coefficients that are easy to work with, okay? So typing this into our function, we end up with a minimum cost of $20,000. So to produce 10,000 soccer balls, to produce and store, the cost would be $20,000. So let's respond officially to minimize the cost to 20,000. We need to produce 10,000 soccer balls. If we produce more or less, that would cause this to increase. Remember, our function here was a parabola that opened up. We have found the vertex here, so if I go more soccer balls or less soccer balls, that's going to cause the cost to increase. So we have minimized the cost using the vertex. Okay, I hope that was helpful. You are ready to begin your homework, so best of luck to you.